We end section 3.2 with rational powers of differentiable functions. And what we're going to do here basically is just update our power rule now that we have a little bit more tools in our toolbox for differentiating. See, we know that the power rule, the derivative with respect to x of x to the n being n x to the n minus 1 holds for any integer n. But with implicit differentiation, we can now prove that it holds when n is a rational number. And rather than go through that entire proof, I'm going to note here that you can find that proof on page 173 of your textbook. So we're going to update the power rule below. If n is now any rational number, rational meaning it can be written as p over q in fractional form, then the derivative with respect to x of x to the n equals n x to the n minus 1. If n is less than 1, then the derivative does not exist at x equals 0. So let's see that in use. Part A, the derivative with respect to x of the square root of x. Well, that can be rewritten since we know that the square root of x is equivalent to x to the power of 1/2. Now, with the power rule applying to rational exponents, we can say the 1/2 comes to the front. We reduce the exponent 1/2 by 1, so now it's negative 1/2. And we can even clean that up a little bit and say 1's in the numerator and 2x to the 1/2 is in the denominator, or we could even call that 1 over 2 root x. So the power rule applies. It also applies in part B, the derivative with respect to x of x to the 2/3. So our 2/3 will come to the front as a coefficient, and now that's going to be x to the power of 2/3 minus 1, or 2/3 minus 3/3, so we can call that negative 1/3. And that will be cleaned up with positive exponents as 2 over 3x to the 1/3. So we have answers here and there. Finally, we'll end with a couple of multiple choice challenges, and I want you to pay close attention to the distractors. When we say distractors in a multiple choice question, what we're referring to are the wrong answers and why those wrong answers might be chosen the way they are. We want to think about why students might choose those incorrectly. So in number 1, if dy dx is equal to 1 plus the sine of y, what is d squared y over dx squared? So what we want to do here is differentiate both sides of this equation with respect to x. I'm just going to note in here d dx. So the derivative with respect to x of dy dx is d squared y over dx squared, and the derivative with respect to x of 1 is 0, and the derivative with respect to x of sine of y is cosine of y. Don't stop there, times dy dx. So there's where maybe part A would have come from. If a student forgot to write in the dy dx there, we may not have moved on where we're going to go now, because we can substitute in place of dy dx 1 plus sine y, since we know that's what it's equal to. So I'm going to write cosine y times 1 plus sine y. And then after the distributive property is involved here, this becomes cosine y plus sine y cosine y, and we see the answer is D. So we know why we might choose A for a wrong answer, and we probably could figure out why a student might choose B if we have derivative rules backwards and think that the derivative of sine is negative cosine. Think about why C might be one of the choices as well, and I can probably envision a student not understanding the notation here of d squared y over dx squared, and might they just think that this is dy dx quantities squared. Is that a possibility? And if so, then that would be why a student might choose C. For number 2, if y is equal to f of t squared and f prime of x is the square root of 2 minus the cosine of x, then what's dy dt? So if we differentiated both sides of this with respect to t, d dt of both sides, since t is the independent variable, then we would have dy dt is equal to f of t squared. We would have to use then the chain rule. So the derivative would be f prime of t squared times 2t by the chain rule. And we see here that f prime of x is 2 minus the cosine of x. So we're going to use that to evaluate f prime of t squared. So if we plugged in a t squared, that would take a t squared into the cosine as well. And now we have, I'm going to move the 2t to the front, so 2t times the square root of 2 minus the cosine, not of x, but of t squared. And I'm looking for that result somewhere, and I'm finding it in part B. And I'm going to challenge you, the viewer, to figure out why a student might choose A or C or D. And you can probably see a few of those answers right now.